Yes. Magnetons. How do they even work? We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might
Yeah,
be just
instead
hyper Rulial Turtles all the way down.
yes, it's on the back of an infinite number of hyperrural turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So the funny thing is when you actually go to the Wikipedia article, again, take that for what it's worth. When you actually search for Magneton, that's one of the things that comes up. Because Pokemon are important. They're people too. I'm just saying. But what the heck are we all talking about here? So we're talking about electromagnetism. This is brought to us by New Scientist. Again, I totally used it primarily just to give accreditation because accreditation matters. Brought to us by Saka Mirskverk from Alami. Oh my god, I apologize for butchering your name. When asking what electromagnetism, one of the four fundamental known forces of nature, does, it is perhaps easier at first to say what it doesn't do. It doesn't keep our feet to the ground, or swinging around the sun and the stars and galaxies in the universe moving on large scales. This is the domain of gravity. At least what I learned from Jonathan, a lot of the equations seem to be very similar. I'm just saying that gravity was curvature. And that's for another video and stuff. But it doesn't bind fundamental particles together in the atomic nucleus or determine the decay. The strong and weak nuclear forces do that. And this was from how long ago? It doesn't matter. Seems like a standard thing. That seems like the standard conjecture and stuff and things. All right. So what are we talking about? What we are talking about here is basically what we were basically just talking about. What am I talking about? Okay, we're going to go over to our fun little equations here because we can. And again, you're going to conjecture. And full disclosure, it looks like they actually updated some of the numbers, maybe reflecting the muon G2 experiment. I'm just saying, depending on our precision and how much credence you give to different things, some of the numbers here are going to be different. We're going to get into that as well. But what am I talking about? We're talking about what we conjecture is a geometric derivation of the magnetons. Okay, yeah, actually, before we do that, we'll go over here. What the heck is a magneton, aside from a type of Pokemon? So, we'll pop back over here. All right. Magneton. Oh, look, as we say, it's also a Pokemon, but primarily we refer to it, at least within physics, as either the Bohr magneton or the nuclear magneton. But hey, Whitechapel, thank you for joining us. Good to see you here. We're gonna get really, really nerdy. But all right, what are we talking about? The Bohr magneton. In atomic physics, the Bohr magneton symbol. Uh, is that new? Or I need to learn this. Sub B is a physical constant, a natural unit for expressing the magnetic moment of an electron, caused by its orbital or spin angular momentum. The Bohr magneton in scientific units is defined as the Bohr magneton from E, which is elementary charge, times h bar, the reduced Planck's constant, and that's all over 2 times the rest mass of the electron. We got the numbers there, 9.274 times 10 to the negative 24. We got our data right here from CoData. Again, all the links in the doobly-doo for anyone that wants to check it out. But, all right, we got that there. And we go over to the nuclear magneton. The nuclear magneton symbol is that new sub N for nuclear, I assume. It's a physical constant of magnetic moment, defined in SI units by nuclear magneton moment of E, which is the elementary charge, times h bar, again, reduced Planck's constant. And that's 2 times the mass of the proton, the rust mass of the proton. What is the rust mass? I think we have a lot of great calculations going into that. Now, and then again, that's times t, which is the speed of light. Now, that right there, that seems like a good calculation. Can we do it geometrically? All right. So we're going to go back over to our little equations over here. So I'm going to pop in here. And again, I am a very lazy person, so I'm totally using the stuff in the thumbnails, so it's easy to get. All right. Here's some equations. Again, this is available in a book, 44 Derangements in the Shape of Persistence. This is currently the 2nd edition here. So let's see what we got. All right. So again, those are the symbols that we saw before. This is basically the equation. Let's get a good bit of confidence in this for the Bohr magneton. This is for the nuclear magneton. All right. What is the equation? This is draw 1. This is what we get from the hyperbolic vortex equation. I think it's the first link in the doobly-doo. So the first answer, you divide it by 2. Apparently there was a 2 in that thing. And then you multiply that by the Planck length squared times the Planck charge times the Planck mass. This is where it gets very confusing because the notation on Wikipedia, again, take it for what it's worth, m sub p was the mass of the proton. This is the Planck mass, according to Thad's notation, as I get a little darker there. Lighting is important. But, oh, and that's what threw me off. It took me like an extra 30, 40 minutes. I'm like, supposed to be 10 to the negative 24, at least towards a magnitude. You want to be within that realm. And it's like, okay, maybe you use more decimal points. But I was at 10 to the negative 99. I'm like, why am I off by 75 orders of magnitude? I was such a noob. I went back to the chart, which I should have from the first. But basically, you divide that all by the Planck time times the mass of the electron, which again, we have a link in the doobly-doo we did a video on the other day. I saw T sub P and I'm like, oh, it's the Planck temperature. That's 10 to the negative 32. The Planck time is 10 to the negative 44. That probably should have been a sign. It's like, why am I off by such a spectacular amount? Noob. IR. And then again, this is the primary action according to the universal binomial equation. So then there's secondary action. Basically, some may say it's the hinged component. We multiply our first action by 1 plus 4b, which is the break in scale symmetry, which is 7. That'll be 28 times E. Euler's not. And to be fair, because we want to be honest in our criticism, that also in the chart that he had, I'm pretty sure it's the same notation for Euler's number and elementary charge. Just we'll do some updates because it confused me too. Because I'm like, what could I be off by? And then that's Euler's number raised to negative 2 pi. So small twist, small circle. And we divide that all by, again, Joe 1, the first answer, raised to the 4th. So some may say it's orthogonally going around. And then the second answer to the hyperbolic vortex equation, J 2 raised to the 4th. Some may say orthogonally arranged. We're dividing all that first part there. And we multiply it like most of these things by our break in scale symmetry, which is the Planck mass times the Planck length divided by the Planck charge squared, which just so happens to come out to be 10 to the negative 7, precisely. Once we do all that, okay, that's pretty cool. So we go back over to our friend. Let's go to our friend Wolfram Alpha. Wolfram Alpha. What is this? What is this complete abomination that I have here? Okay, that's that Joe 1 squared divided by 2. And we multiply it all by, again, Planck length squared times the Planck charge times the Planck mass. And again, the reason those are normally negatives, that's why it's dividing it by the exponential factor. So that's essentially the same as division. And then again, that is over the Planck time, not the Planck temperature, or else you'll be off by like 75 orders of magnitude. And this times the mass of the electron. I guess that's that rest mass part. And again, we multiply this all by terminal action. 1 plus 4 times the breaking scale, symmetry 7, times Joule's number, raised to negative 2 pi again, so little twist. And that's divided by Joe 1, first answer, the hyperbolic vortex equation, raised to the 4th, times the second answer, the hyperbolic vortex equation, raised to the 4th, and then 10 to the negative 7 again, you would divide it by that. It's going to have to be this number here. Okay. There's going to be a little deviation here because it looks like they updated it. This is 9.274009. All right. Go data from physics.nist.gov. All right. So numerical value is 9.274010. Again, there is a slight deviation here. Because at least the number Stat has in the book when he was looking at it out. And again, maybe they had updated it. The other thing is, I'm not sure if I noticed this thing before. Look for the correlation coefficient in this constant with other constants. It's interesting. Okay, so 2.74, and that's times 10 to the negative 24. And the error bars, 0.28 there. So if we were to go up that or down, it might. We'll change it a little bit, but again, this was updated. Perhaps this is one of the reasons why I'm an intern, because Dad doesn't need to do all this stuff again and again. That's the way he taught people like me. Maybe I'll do it this weekend. But all right, so there's 9.27401, 9.274009999, and again, Thad using an extra couple of things, so it's I think that's maybe a 3 there. His derivation. Again, we can use as many decimal points as we want because we have geometric derivations for it. Okay, and again, the Joe 1 there. That's this right here. This is the second answer. Again, first and second answer. First answer. Mass of the electron we calculated here the other day. Excuse me, this is the rest mass of the proton because that's 10 to the negative 27. Mass of the electron is here. Yeah. 9.109 times 10 to the negative 31. And that lines up with all the significant digits within the margins of error. Now, again, there's a little deviation. This is why experiments are important. Do we need a bigger collider or better detectors? I'm just saying. But, and we'll go back. What the heck is the nuclear magneton? All right, so we got that little logical, using a little bit of algebra and some calculus there. Can we geometricize it? Let's take a look. All right, we go back. Oh, and of course I closed it, but no, we don't need you, Magneton, but it's all right. You're cool. So again, this is the fantastic part about this whole thing. Okay, so it's literally the exact same equation. The one thing we change, again, kind of like in the other one, it's instead of the mass of the electron, we use the mass of the proton. Other than that, everything else is the exact same. We got our circle there. We got our geometric derivation from the hyperbolic vortex equation. Things are orthogonally lined up. Now, again, I realize I wasn't sharing right there. Terrible person. Okay. So again, these are exactly the same equation. So instead of the mass of the electron, we have the mass of the proton there. That's the beautiful thing. Again, our pi twist geometric derivation from the hyperbolic vortex equation. Okay. So, if that were to hold, that would mean I can be a pretty lazy person. Go back over to our friend Wolfram Alpha. Okay. Look at this monstrosity actually typed out, and actually all the digits fit in there. That was actually a very positive experience. I'm just breaking up different things. I need to learn how to use Mathematica. Okay, so okay, mass of the electron. Take the mass of the proton. I'll click on that. We got like 13 significant digits there. We copy it. Okay, so that's the mass of the electron, so that's 10 to the negative 31. Okay, oh god, that was a bunch of digits there. All right, over. Why are you? Oh, we're lagging. Aren't we? Oof. I think I need a new computer. No. Oh, snap. Something went wrong. Oh, no. What shall we do? All right. Good thing we bookmarked this. It seemed like a very useful thing to bookmark. I'm just like, oh, there we go, board Magneton. I had to just put this all in a notebook. I need to bite the bullet and do it. All right. So, over here. All right. We throw in the mass of the proton again. Need to clear it up. Negative 27. All right. Boom. Boom. I'm sorry, I'm listening to Dragon, but it took me so long. By the time I figured this out and set most of this up, I'd already gone through my hour listening to Ultimate Battle. It's a good tune. What's this? 5.05078. Go to our friend, physics.nist.gov. 5.05078. Hold on. 7836. 7837. Again, a little bit of a discrepancy there. Times 6 times 1 5. Now, again. Oh, it doesn't line up. It doesn't line up. I'm just saying a lot of these other numbers lined up, and what also kind of gives me hope is some confidence in this. It's because even the whole thing that got me into this, yes, bookmark backup, and again, that's why I put in these videos, so I just can go back and basically just grab everything Whitechapel. You're totally right. But the big thing is we have a method. We literally have a cartography method for physics right now, in that we can search the computational universe. Because like the whole thing was, I listened to this because Nolan had. They're like, oh look, hey, had some hip hop and Thad Rupp. So okay, follow that. Oh, I just happened to click on this thing. Okay, it's like, oh, that's a lot of claims. I'm like, well, if half the stuff this dude's saying is correct, this is revolutionary. But I'm like, take it with a grain of salt. I'm like, it's a dude on the internet. I'm a dude on the internet. And then the very next day, they released the Muon-G2 results. And it's like, okay, listening. I'm like, oh, it's our Mars rover moment. I'm like, all right, that's apparently this is an important experiment. Oh, we confirmed what Brookhaven had. Whoa, that's cool. I'm like, all right, nifty. I'll tweet at that. Does this help your model? Yes. Go home. Look, look at the results from Fermilab. I'm like, all right. Go back to the video that premiered the day before. I'm like, dude, man, nailed it. Was like 13 significant digits or something like that. I'm like, all right, that's pretty cool. He predicted the UNG2. See, that thing is because in the second edition of the book, I'm like, wait a second. This equation is different than what it originally was because there were a bunch of sevens and breaks and scale symmetry and that like mixed up. And then the next version, some may say it got more beautiful because that had some more significant differences to explore. It's like, oh, so basically some of the breaks and scale symmetry ended up changing to, I think, Ramanujan's function or something like that. What it is, because one of the most famous physicists, that's like, oh my god! I think he has his own physics center or over, and I watched some of the things from one of the centers for theoretical physics, and I think they had it in like the Ramanujan lecture hall. I'm like, all right, oh, it seems to be simpler. Cool, but and again, it's like the more data we get, the more we can explore, and I'm just saying. We have a method to map the road ahead and our realm of persistence. I'm pretty sure at the minimum, it'll at least have us get a lot of really cool video games. As someone that's been more or less a lifelong gamer, I think that's pretty cool. But that's all I for right now. I see you there, Wise. Thank you for. I got your name right. See, I can learn too. Can teach this Scaly occasionally some new tricks, but peace out, everybody. Be safe, and again, rumor has it 2023 is the year to see. Peace out, everybody.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like